Hi everyone, I'm Ta-Shun Chou. So as I mentioned, it's like I'm currently the postdoc in the Leibniz Institute. And actually, before I was studying in there, I also studied my master degree in Erlangen. So actually, I'm very happy to be back, but usually I'm in another campus. So it's the first time for me in the Physics Institute. So today I'm going to share some of my, user experiences in the past 1.5 years, that how we use the NOMAD system to manage all the data generated by MOCVD system when we want to develop the gallium oxide thin film process. Yes. So yeah. So before we dive into how we manage the data, I will give a little bit overview about what we are doing with gallium oxide. So you have a chance to know how complicated our daily life is and how NOMAD can help us to make our life easier. So just a very quick overview, what is beta-gallium oxide? Beta-gallium oxide is actually the monoclinic structure with the several cleavage plane in 100 and 001 plant. And the reason why we are so interested in this material, because this material has a certain excellent physical property, which make it suitable for high-power electronic application. So this material has very wide band gap, up to 4.8 electron volt, and it comes hand in hand with high beta foam figure as well as the high breakdown field, which make it a very strong competitor to silicon carbide and gallium nitride when it comes to high voltage application. And of course, it comes with some other, advantage. For example, at the same time, you can also have the very low power loss when you use the gallium oxide based, device. And also, beta-gallium oxide is currently the only one wide bandgap semiconductor material which can be grown from the melt, which has a high potential to be much cheaper than gallium nitride and silicon carbide. And that's the reason why we are so, interested in this material. Yeah, of course. So it has, as I mentioned, it has an application in very high voltage fields. Yeah, high power electronics. And our daily life. So if you want to use this material, so once you have the high quality substrate, our next target is actually how you need to grow a high quality thin film on top of the substrate. So later on, people who are working with device can take your epitaxial wafer, start to fabricate a device, and gradually move into their market site. So our task, we are actually the research group using MOCVD to grow the epitaxial layer. So in the past, 10 years, we actually figure out some key factor. For example, we know there are actually 3 morphology: island growth, step flow, and step bunching, which actually determine the quality of the film. So usually we want the desired step flow morphology allow us to have the minimized structural defect and best electrical property. And so how to control it, we figure out a little bit. So we know we can apply the substrate miscut on the substrate to control the terrace width on top of the substrate. And at the same time, by manipulating all the growth parameter in MOCVD, we can control the gallium at layer diffusion length. So by matching these two, factor, ideally we should be able to get the step flow. Yeah. So, but very quickly, and we face some problems. So actually, there are some problems of the morphology instability, like balanced Schwann field instability, and step pinning by dopant or impurity. So we face these 2 problems, and we're struggling a lot to try to figure out how can we adjust the parameter to overcome this problem. And luckily, we realized that actually in our past experiences, we identified 3 growth regions to control different morphology, but we end up finding that actually there's a 4th growth window, which will give us even better result, and we didn't discover before. And therefore, as a sum up, is that so at the end we find out that simply by playing with oxygen to gallium ratio, by providing a more gallium-rich environment, we are able to largely enhance the diffusion length of the gallium at the atom and improve the stability of morphology. So it ends up with that we find a additional growth regime, which is highlighted by the green rectangular, that under this regime, we're able to produce the high-quality film for different applications. So this is a very quick overview about what we are doing. You feel like, yeah, so it's easy, right? To play one parameter and everything is done. But this is the bright side of MOCVD. What is the dark side? And the dark side, which is actually, so in your left-hand side is our MOCVD equipment. However, to achieve, let's say, the high-quality films or to find the proper growth window for MOCVD is a time-consuming and labor-consuming task. So in the middle, you can see that our daily life is that, okay, we find, based on our educational guess, we find out a set of parameters. And this set of parameters can consist of maybe 10 growth parameters: temperature, pressure, rotating speeds, the ratio between different precursor, and for example, the gas flow in the chamber. Each parameter will have influence in your layer. The final property of your layer. And then by set up a one parameter, then you grow a layer, and after the layer is grown, you need to do a series of the characterization, FM, SEM, XRD, whole measurement, try to figure out what is the property of this material, and then you go back to consider what is the mechanism, and then 9 o'clock in the morning, you figure out another possible set, and then go on and go on. So every day you change one or two parameter, and actually it end up, you probably need more than 10 years if you try all the combination and find the proper growth window. If we don't, let's say, figure out what's the growth mechanics, or we don't use other way to help us. So this is our daily life, and this kind of daily life actually face some difficult challenge along the time. So basically, there are 4 challenges in our daily life, or let's say in our research group. Let's say the most important, the most difficult, the biggest challenge is that people comes and go. So postdocs stay for 2 years, PhD student stay for 3 to 4 years. But once people graduate, all the knowledge are lost. So when I joined in 2020, I have no idea what happened or what have been done in the past 7 years. Luckily, I have the COVID for 3 years. I can stay at home to really dig out all the data set. But this is really a big challenge in most of the research group. And when people comes and go, it comes with 2 other problems. Is that, yes, as I mentioned, knowledge lost. Many results make no sense for a newcomer. Second, every people has different way of manage data. So you end up with a very complicated or very messy data management. So, for example, when I come, there are many TEM and SEM or SIMS measurement. I don't even know why people do that. For me, it makes no sense. And it will make a huge barrier for people to pass in a knowledge from, we don't say generation to generation, but from one PhD student to another PhD student. And this is actually our daily life. So in the left-hand side is when I join. When I open the folder, I see different folder with different kind of name and different definition. I don't have no motivation to open any of them and check. In the right-hand side is actually a specification like only for SIMS data, people do not organize in a very well way. And what's not mentioned is that there are many handwritten notebook, let's say, distributed around in the lab. It actually this is actually a big trouble. So our first approach is that we try to extract the knowledge from this old data set, from this messy data set. So the one thing is that we recognize is it's impossible to really understand the result for each parameter we tried in the past. So what we have done is that we actually try to organize the Excel sheets which record the parameter in the past, and we use machine learning try to extract the knowledge from all the data sets. So we actually, in 2 years ago, I started to use the random forest algorithm. I applied to all the Excel sheet we accumulate year by year, and then we are able to use this growth parameter combined with algorithm, try to predict the growth rate, doping level, and morphology. We try to conclude in all parameter combination, which parameter is most important for growth rate, doping level, or morphology control. And in the right-hand side is actually the workflow we try to establish. So yeah, we try to condense the knowledge for the newcomer. And after we met FAIRmat, the life become more and more easier because we all know that the machine learning relies on structural data set and let's say label data set. So in the left-hand side is how we organize data, let's say for decades. So we have different folder contains a different growth parameter. We have the different characterization, AFM, light microscopy, SIMS, scattered around in different folder, and we have a different Excel sheet which contain all the parameters. So this is how we distribute the data in the past. So we can imagine if you want to check what we have done in 2017, I think you need three screens to open all the folder and understand what people have done in the past. But now with the NOMAD OSs, we try to organize all the data in same place. In the right-hand side, you can see that. So we start to structure all single growth recipe into one single entry in the NOMAD OSs, and then try to put all the information together. And by doing so, we are able to, as your right-hand side, we're able to collect all information from the substrate, from the growth rate, growth recipe, from all the characterization data. They will be all in the same place, and which allow us to use it, say, more efficiently, as I will later explain. So here, just to show that by putting all the information together on NOMAD OSs, what kind of benefit we can have. So basically, we can put all the information we want to know regarding our process. So basically, nowadays, we're able to put all the substrate information in NOMAD OSs. We are also able to put the whole life cycle of our sample, let's say from before the growth start, after the growth, even the treatment in between. We can put all the data together to ensure we have overview about everything. Yeah, and then which include naturally the growth recipe of each growth round, and also the in situ monitoring data we collect during the growth. Everything can be put in the same place, and we are able to do the characterization all at the same time. Yeah, and yeah, as I mentioned, all the characterization like the let's say image data, also the numerical data, they will be all structured now in the NOMAD OSs. And as part of our final goal is that with all the data structured and organized in the same place, then we are able to really use the machine learning to extract all the data, and we are able to do prediction, classification, and we are able to learn more about our data set instead of one-by-one comparison in the Excel sheet. So here is actually just a part of our current NOMAD OSs structure to store our emulsivity data. So basically now we are able, we will actually we will write down, for example, the data, the information about the time, so we know when do we do the growth round, and we are able to say, usually in emulsivity is a mass production machine, so maybe we'll put 2 to 4 substrate at the same time, and we are able to so we are able to let's say classify each single substrate in one growth round, and we are able to save the data for each substrate, let's say separately, but they are all in the same structure. Yeah, and with all the data, layer, another thing we can do is that we are able to track the life cycle of our sample, because as we mentioned, our goal is to do the device. Therefore, they say simply growing the film is just 50% done, job done. So later on, we may do annealing, we may deposit electrode on the top, we may do some cleaning or etching afterwards. All this step will be recorded as a life cycle, and then we will put them all together, and we know, so even after 3 or 5 years, we come back, we will know, okay, I have done annealing and etching on a sample, on this specific sample, and that is what we can benefit from. Yeah, so here is actually an overview. It's like, so what we are, by doing everything now, how we interact with NOMAD. So with NOMAD in the center, we not just store the data in this platform, which also allow us to do the further data analysis with the external Python script or the online Jupyter notebook. And then we are later on, as a final goal, we are able to connect our data with the measurement data from other group, or we're able to share the data with the other group. Yeah, here is just some other example is that there are some new function we are able to perform on the NOMAD OSs together with the member in the FAIRmat. So, for example, this is actually one example about our self-developed algorithm to process the in-situ monitoring collect from the MOCVD algorithm. So basically, you're able to calculate the growth rate from during the growth, and we developed this algorithm, and with the help of the member from NOMAD, we are also able to transfer this algorithm to the NOMAD OSs, and then people who are using the same equipment, same data, in the future, they will be able to benefit from our development with this uniform, let's say, integrate into platform. Yeah, and since we mentioned machine learning several times, and we also did some machine learning, but the next step, or let's say, what we think that the most what we can benefit from the NOMAD the most is that we are able to do the online machine learning, and let's say we are able to interact with all the data we save on this platform. So this is actually a Jupyter notebook developed by the Satak. Yeah, with Satak. Yeah, yes. So he wrote me. He actually tried to integrate some machine learning algorithm here, and then with this Jupyter notebook, we have access to all the data we save on the NOMAD platform. So before, so in a daily basis, we will write down the growth rate, we will write down the morphology, we will write down the doping concentration of each theme we grown in the past. Then, with this Jupyter notebook, we are able to collect all the data there and put the machine learning algorithm on the top, and then it will output the result as we do before that. For example, as I mentioned, we use machine learning to predict the growth rate, doping, and morphology. And we are able to, for example, with machine learning, we can do the parameter ranking. So, for example, algorithm tell you, now we are able to predict the growth rate very precisely. And random forest can also tell you another information is that why we are able to predict it, let's say, precisely. Then, based on this parameter ranking, they tell you which parameter is the most important for your desired physical property. We are able to learn some, with our physical background or educational background, we are able to guess some hidden mechanism behind the parameter ranking. And what I want to address here is that once you figure out a certain mechanism, you are, as I did here, I also collect the parameter from other group in United States. I am able to verify their data in my model. And as you can see that, it seems that there's the same physical rule in all MOCVD in the world, and that's and that is how I can foresee if everyone in the world, ideally in 10 years, everyone is using FAIRmat, people using same method, they're able to interact or exchange their information in a similar way. So. With all the experimental work and with the help of the NOMAD structure and the, let's say, rise of the AI mechanism, algorithm, this is the idea or utopia where we can imagine for. So as an MVP researcher, they said hopefully one day the MOBP engineer or scientist, they can sit in the center. They are able to use the MOCVD machine with the generated data. They insert or upload to the NOMAD platform. And with NOMAD platform, you can actually apply AI machine learning on top of it. With the learned knowledge from AI and machine learning, you are able to give the feedback to MOCVD. And this will be for me, let's say, the ideal world for MOCVD researcher or engineer. And most importantly, this workflow can be transferred or shared with the other, let's say, researcher. They are using similar or a different technology. So I want to summarize my, let's say, experiences and share some, let's say, some foreseeable challenge I had in the past 2 years when I tried to promote NOMAD in our institute. So first of all, my feeling is that using NOMAD is actually doing quality control or build up a knowledge library for your research data. So when I recall my educational path, I do not have the proper training, or nobody told me that how to do a quality control for your research data until before I'm PhD, I joined a company and I somehow learned that how to use some statistical way, how to build up a statistic on the production line, and then that is actually a very similar idea as NOMAD. And second thing I want to share is that, yes, I think everyone knows that FAIRmat is a long-term benefit, but this is the conclusion. This is also a challenge because it's long-term. As I mentioned, people tend to come and go in the institute. So it's very hard so if I'm a PhD student, I stay only here for 3 years. I tell you, there's something which is good. If you do it, you will benefit people in 10 years. Good to have, but thank you. I will publish more papers so I can graduate. And this is actually, I think this is the challenge, let's say, we face now. So it's very difficult to motivate people to put more time on this platform. Everyone said this is good, but people used to prioritize other tasks on top of their FAIRmat task. And the third thing is that, yes, we mentioned about many bottom-up approach. So it's very important that for the newcomer to the lab, we should start to let's say, introduce them the new tool, digitalization tool. But in my past 2 years experiences, I also realized that the top-down influence is also important because you need someone from your boss or from the management level. They really appreciate what you have done because they say maybe I spend they say 20% of my working time in FAIRmat, but at the end of the day they just ask how many papers you published last year. Then it actually demotivates people to do that. And so this is just my experimental sharing, and it's really very personal experiences. And hopefully later on, if you have any question, we are happy to. I'm happy to share more insight with you. So I will stop here. So there's still 5 minutes for Q&A.